Welcome to AI driven perception, learning and mapping for drones. Introduction lecture is a continuation. The previous lecture we talked about the different applications of the drone. We talked about the need for AI in drones for perception, learning and mapping aspects of it. In this lecture we will talk more about the history, breakthroughs, right, and the future ahead in the drones, so that it just provide why we need to look into foundations of neural networks, foundations of convolution neural network, recurrent neural networks and generative AI for perception and planning. Now when we look at history of deep learning, let's try to understand what started first, right? The basic neurons. It's a fundamental building block of the entire neural network, which receives signals from sensory neurons, and these signals are transmitted to the cell, right, where things get amplified or suppressed, and the output which comes out, it's been passed on to the subsequent neuron. This is a building block of it. We will study more about it in the module 1. And the first time in 1943, McCullough-Spitz proposed the neuron model inspired from the basic neuron, and most of this is talk about how this basic neuron can be used to solve simple logic gates like AND or NAT problems. We will discuss this when we go into foundational neural network. I am just trying to connect you that how it is built. Then the Rosenberg introduced perceptron and how these weights of these neurons can be automatically learned to solve the problems. Then comes multi-layer perceptron, then comes the other radial basis function, recurrent neural networks, self-organizing map and so on and so forth, and it can be used for function approximation classifications. We will discuss in more details when it comes to the foundation neural network module. But then the challenges came which introduced a breakthrough in handling the images. Earlier the images people used to extract features, and these features are used for learning purposes. The ImageNet challenge, basically the classifications of close to 1,000 objects. Each object was manually labeled by a human being, and then how this can be learned automatically to recognize different objects like flamingo, quail, or cat, different types of cat and so on and so forth. This introduced challenge in terms of handling a large number of classes and building an end-to-end system by just looking at the image to identify them. That brought in newer versions of the algorithm. Between 2010 to 2020, the convolution neural network started gaining a lot of attention and then started solving the problems much more efficiently. Instead of using handcrafted features, almost for 50 years people extract features from them, and then the features are passed on to the neural network to classify. Automatic learning of these features came into picture, the accuracy started improving further and further, right. This breakthrough is possible not just because of the algorithmic development, also because of the computational power that is being available. So the deep learning architecture, if you look at, it not just required data, it also required computational power and the learning paradigm which to help to extract information from the data, right. What we had earlier to today we have a big large GPU clusters with high power computing capability, right. The compute structures are improving a lot and which helps researchers to build a much deeper network, huge neural network which can just generate as close as possible to real data itself, right, real image itself. Now when you look at this, the history of growth, and also history of usage of the drones also changed. Earlier we were looking at applications where one goes and look at agriculture, or one look at surveillance aspect of it, inspection aspect of it, right? Think about it in a world where future is with lot of drones flying around like our cars, and it seamlessly integrating with respect to the traffic network, which was an illustrative figure from NASA for you to understand. The challenge is going to be multifold, right? What is the challenge? The traffic is always a peculiar. The traffic, what we call as a non-stationary in nature. The kind of flow varies over a period of time for many reasons. Suddenly if there is a cricket match, you will see that nobody wants to go, and particularly if it is an India-Pakistan World Cup match, and nobody will be there on the street, right? So depends on the context and the scenario and situation, there is a likelihood of change in the traffic pattern. The most important thing is the safety and reliability. We also have to handle the distribution shift which can just take place. So what is more important is how do I plan my route? How do I handle obstacles if there is a crisscross traffic goes into picture, right? What to give importance? Where to introduce the landing pad? Where to introduce the crossover regions? How do I monitor the flow? All that becomes an interesting problem because of advancement in AI made these drones to operate autonomously. I can identify the rogue drone, I can identify the drones which is behaving differently, and I can introduce the safety, reliability can increase. If the reliability increases, people start using for mobility purposes, right? Now the challenge comes into multiple drones are free to fly. There are different actors in the scene, right? The birds, these are not cooperative in nature. There are drones which can be cooperative. Suddenly this connection between the operator and the drone is not there, and it's still also called non-cooperative actors. You can have a centralized decision making capability in urban traffic management, right? Initially the drone follows the predefined trajectory prescribed by the UTM operator to go. But there are factors which can affect the flow of it. Wind variation comes into picture. Because of the wind variation, the time you reach the destination might change, right? You may have to slow down. So time, at what time you will be at what location might vary. The noises in sensor, which is also going to add a factor to when you will be reaching there, right? Because of that, there is an uncertainty in the velocity. What I meant velocity is uncertainty in the time of arrival to a specific location. So you may have a conflict. You may have a conflict because suddenly there is a huge traffic piled on the road, and I don't want anybody to fly over that. Then that becomes a no-fly zone. You cannot enter. Then you have to reroute yourself. You can have a conflict between two drones. There could be a collision. Sudden change in weather, right? That can also add a no-fly zone. Because of the routes has been changed, and you may have a conflict with other zone. So you have to do reactive planning. You also have to do predefined planning in such a way that you don't collide with others, right? So for example, I am just giving a simulated environment for you to understand. If this is a roundabout in which the drones have to come, when they come in there is a conflict, suddenly these roundabouts come into picture in the air, where you just kind of enter into the roundabout and move away and to reach your destination where you want, right? These are kind of a virtual islands. When there is a conflict, these roundabouts comes into picture. When there is no conflict, these traffic islands are not there. You are free to fly straight from one point to another point. How do we bring this roundabout? How do we monitor them? These all become an interesting challenge when, because of these advancements, newer problems comes into picture. The newer problems are the newer challenges for us to solve, right? Then sensor development. We suddenly have various sensors is available, right? For example, depth sensor is there, event cameras are there, LiDARs are there. These are complementary sensors. These complementary sensors going to give information about the context in which you are going to fly. If there is no change, event camera will not give you any information. So how am I going to use them to understand the semantics of the scene, right? How am I going to simulate the real scenarios which is changing because of the advanced developments? How am I going to generalize my domain when you have the different complementary sensors present, right? Sometimes you may have all the sensors, but one of them suddenly will not be present or failed, right? See, it is not like GPS alone denied environment, it can also have sensor denied environment. Your event camera may not work in that particular environment, then you do not have the data. When you do not have the data, how is the AI going to take a decision to understand the scene, right? How am I going to generalize with respect to the change in weather and geographical conditions wherein this is going to be present, right? These are going to be an interesting task, right? Like a RGB camera and a depth camera and the event camera gives a different informations, right? The LiDAR gives a different information. How am I going to combine all of them to learn to understand the scene or the context in which I am present and act on it? And this also brings in interesting challenges, the clutter in the environment. There could be unknown target, the domain could be changed completely, data may not be present in that particular domain, and we talked about this, right? It could be night, the predictions in the night can just go bad. The data, the network is trained on one domain and tested in another domain, can it generalize? How it can just understand this domain and apply the learning more efficiently? It is going to be a bigger challenge. Data scarcity. I may not have data in all scenarios, right? I may not have a data for sunny, foggy, rainy, snowy and night. For example, in your city it may not you may not get snow, right? It will be more hot, more rainy possible, right? So when you have the variations comes into picture, I may not have a sufficient data in all the domain. How do I generalize my learning with a minimal effort? It is more important, right? How do I use generative modeling to perform the downstream task? What we mean downstream task is a classification or segmentation much more efficiently, right? To just give you an understanding how the research is taking place to make the network to more generalizable even at different scenes, how they are improving with respect to generative data, how it is helping the generative data to understand the scene and generalize better. See, perception beyond a visual spectrum is also very important, right? For example, if you look at the acoustic side scan sonar data, the sonar data can just talk about what is present in the surface in the water, right? That is also perception. You may not have sufficient information about shipwreck. You may not get it at a different salinity levels, right? How the data going to be generated and how can I use the generated data to learn, right? Same goes in IR imagery. I may have a lot of data in RGB modality. I may not have sufficient data in IR imagery. You need more data. Can I get the mapping between these two and generate more data, use that data to learn, and then I have only fewer samples from this real domain, use it to refine it further so that I can perform better or robust visual perception. Now, the onboard computing capability increased, different sensor modality has increased, then use of swarms for a specific problem is also increasing. Then the challenge comes in how AI is going to play an important role in this. If you look at a UAV swarm we always say it has a collective intelligence, right? It is a distributed sensing comes into picture. Even when one fails, still it can operate. It is more resilient in nature. Multiple perception can help me to understand the scene much more better, seeing better than a single perception. Robustness comes into picture. This have a collective behavior, right? They fly, they share the information in the local neighborhood, that gets more robust for understanding it. They can cooperatively track the target, cooperatively act on the environment. But there are a lot of challenges. They are operating in adverse conditions, where they are trying to observe something in the adverse condition. The moment adverse condition comes into picture, the scenario is not stationary. Scenario is changing, or the distribution present, the way the target move in this is changing with respect to time. If there is a flood, there is a survivor, we cannot say how the survivor will be in the flood. The course of the water is not clear. It can go anywhere. It can be pushed left and right, depends on the course of the flood, right. It is difficult to track. So, how I am going to observe the scene, how I am going to act on the scene is going to be different. In such scenarios, we need a swarm of systems, so that there is a collective intelligence, there is a resiliency, because there is a multiple perceptions. I can have robustness in understanding the scene more efficiently, right. Most of the use cases of swarms are search and rescue, right, where we are trying to localize the target, where we are trying to map the target, or we are trying to track the target, such that we can provide necessary assistance to these targets and rescue them from the adverse situation, right. What kind of problems comes into this category? Perimeter defense, confinement escape, large area surveillance, forest fire, search and rescue, target tracking and monitoring, convoy protection, large area inspections, all comes into this category, right. So, we talk about convoy, this is a convoy, confinement region. If someone enters into this region, I want to monitor, track them and capture them, right. These are the very interesting problems in which drones has been used significantly. But it has challenges. What are the challenges? Sensor uncertainty. You may not see them completely, partially observable scenario, right. You may see it, I may not see it. If I can't see it, how I work together? Now, the second challenge comes, which sensor to be used for that particular scene. Sensor denied environment, it is all adverse condition, right. If think about a smoke and I go with an RGB camera, the smoke comes into picture, I cannot see the scene. How do I identify the survivor? How do I use other modality in such scenario to see the target, right. So, that leads to a question, what to use, when to use, how to use. The other problem is the target nature. We do not know the type of target, we do not know the location of the target. Even if you look at the survivor, we do not know whether it is a well built or nominal, or is it a children, we do not know, and where they are we do not know, right. It is more heterogeneous in nature, they are very highly agile. The resource requirements for the number of target present may not be sufficient, right. Those are the challenges we will have. States are uncertain. Adverse condition, which means denied environments, sensor denied environments. So, there is a uncertainty in your position as well as the target positions, right. Now, these uncertainty add challenges in computational uncertainty. Task nature, right. Is the task is spatially and temporally connected. It can be handled by the single robot. It can be handled by multiple robot. When I say multiple robot, it can be simultaneous or sequential, right. All of them have come together and quenched the fire. If you are looking at survivor, all of us have to come simultaneously to lift the person from the scene to another location. Sometimes you can go in sequential, You can drop water, you can drop food, right? It's fine. You don't have to drop everything simultaneously to the target so that they can survive in the environment, right? So actions are different. How do we do it? And we have a limited resources also to take decisions and onboard. It's not like I carry a big GPU cluster with me and which can compute and make the decisions. Computational resource is also limited. How I am going to use it? Shall I send the entire data to my neighbor so that he can make decision, or shall I share the processed information to me? The scalability, reliability adds a challenges, right? One domain to another domain, uncertainty differs significantly. How am I going to handle that, right? Consensus in cooperations is needed. The consensus should be domain independent of that, right? Of course, there are other challenges like a communication uncertainty comes into picture. What is the range of communication, bandwidth, connectivity that I could have in those adverse scenarios is always a challenge. Execution challenge comes into picture. The decision space are not fixed because I don't know the type of the target, I don't know what type of task I have to perform, I don't know the decision space upfront. Sometimes I may have to come together in a specific formation, right? How am I going to get it? I may have to actuation mechanisms to act onto the scene, right? So that all adds an uncertainty in RL, in Swarm for a specific application which requires reinforcement learning kind of a mechanism. Unless you recover someone, there is a reward, otherwise there is no reward. There is no supervision here that I can just say this is how it is going to be, right? So reinforcement learning has been significantly used in such scenarios. We will introduce some basic concepts of this and how to use it. If you are interested more about it, you may have to take a course on reinforcement learning itself, right? That's when distributed autonomy comes into picture. Now, what are the future research people are doing? I just want to connect here because even though it's a course, we need to understand how the world is moving ahead, right? The vision and language models are combined together significantly, right? I have a data in the internet, I just do the pre-training and get the world model and understanding of that, and how I use that to handle out of distribution data. The data which is not present in the pre-training level, right? How I can use this for better generalization for an unseen target domains, right? I am just trying to give you a correlational of out of distribution performances with and without vision models for you to get it. In the same domain, the vision models performs better, but when you look at out of domain, vision and language combines together is performing better, right? So out of domain, when you want to do a better generalization, it's good idea to bring in vision language models together to handle it, right? So if you look at pre-trained standard data set, better in their own domain, and when you have other domain, the performance becomes lower. Whereas if you look at it from the perspective of VLMs, their performance is far better. But then certain tasks are very common where I need a foundational models, right? I want something to be learned which can be used for many tasks. These tasks can be divided into subtasks. These subtasks are very common across most of these complex tasks. Can I have a foundation models? This is more like a foundation models for complementary modalities, right? I have the LiDAR scan, I can do the 3D mapping of that, I have the image, and how do I combine these together to understand the scene better? Or I can just talk about autonomous system into picture. Different scenarios, dark, bright, snow, fog, rain, right? You can have a different lenses into picture. There is a blur, motion blur comes into picture. You have a different quantization mechanisms into picture, different text into picture, right? You can have situations where your sensor gets saturated. Suddenly your frame rate frames are not proper. So you can have all kind of scenarios, right? You can ask question, what is moving in this particular scene? What speed or what steering angle at which this is going, right? So you can have all kind of variations and language put together. Language also helps in terms of behavior, and it also helps you to, the combination of that helps you to predict what's going to happen and helps you to plan better. So a lot of people are looking at a scenario like this where we can generate data to build a foundation models for autonomous systems to operate. Whether it is a ground vehicle or aerial vehicle, it's all the same, right? Only thing is the kind of foundation models that we are looking at an operation in 3-dimensional space comes into picture. Some of these actions that you are performing on the ground may not be true on the air, so we may have to look at it. But foundation models for complementary modalities is what is going on in the current research. Not just only vision language actions comes into picture. Actions to understand, right? I could have sensors, visual sensor, I have a description, and with that I need to perform actions onto the scene, right? Think about it, you have a sensory motor model, you have a world model, you have affordance model, and you have a different learning mechanisms available to you. Somewhere you have ground truth data is available, so you can do supervised learning. For some you have annotation, some you do not have annotation, so you may have to use self-supervised learning. For some scenario I do not even have data, but I can give you reward. If you perform this task, you will reward. For example, if you leave from your hostel, reach your classroom, you can get a reward. Reach them on time, you get a better reward. Reach late, you get a negative reward. So that is how it works. So you have different mechanisms into picture, the vision, language, action gaining a lot of attention. You have different type of manipulators, right? Gripping, you can have spraying, right? You can have different type of physical systems too. Recently the research started looking at hybrid systems, flying and going on the surface of the water or slightly below the surface of the water, flying and walking, right? Hybrid systems. So how do you collect data on different scenarios? How do you generate this kind of a data set? What perception is doing? Perception, when I say, is not just RGB, right? Understand this could be radar perception, LiDAR perception, right? Complementary modalities, all these are complementary modalities. I have a language and I have actions to be performed, and that is how I can build vision, language, action model, foundation models for that. That is how research moving towards, right. Now coming to autonomy perspective, what we used to do is we divide that into hardware stack and software stack. In hardware stack you have of course a physical system being present, you have actuator, you have sensor, your edge computer and controllers sit in. In software stack you ask questions, right. I assume the drone is capable of maintaining the speed and track the trajectory. But the challenge comes is understanding the external environment, understanding, that is a perception, right, contextual understanding. Identify the target, and if I identify a target, is it an obstacle? Obstacle requires your path and the path of the target should coincide. If there is an obstacle, right, spatial temporal relationship comes into picture. Then I need to generate a path. That path need to be modified. The research directions now, we used to do this, perception operates at different speed, whereas the inner loop control operates in very high speed, right, planning operates at a different speed. Now the question comes, the advancement of compute capability, I do not really need to understand the environment, identify the obstacle. Given an image, can you tell me what action I need to perform? It is more like end to end learning for navigation purposes, right? That is where research is going on. Also people look at general intelligence, right? We understand the neuron, we brought in a deep neural network structures, but we start to ask questions. Can I have general intelligence, a general knowledge? Can I possess a general knowledge about the world and can solve list of problems? I am not talking about solving all possible list of problems. Some could be not in my own distribution. Some better higher level of cognitive skills, ability to understand the context, the relationship between different phenomena and abstract a common sense reasoning from that. It is also in another area, right. Goal redirected, learn and decide or guided, decisions are guided based on the goals. Ensure a specific purposeful behavior, right. Can I do that? Can I learn continuously? When we learn continuously, there is always a problem of catastrophic forgetting. Without forgetting, without affecting my learnt knowledge, can I learn continuously? And robustness in learning is also an important. Robust generalization is the biggest problem. Can I perform better in all domain? How do I perform better in all domain? It is all challenges people are trying to address such that we can provide better autonomy, better distributed autonomy to solve complex problems. In a summary, this introduction lecture covers different applications of the drones, and that motivates why AI is needed for perception, planning and distributed control. What kind of challenges that one would experience when we talk about multimodal perceptions. Moment we talk about distributed AI where the scenarios are changing adverse, there are a lot of challenges in terms of sensor, computation and decisions. You cannot do it, and distributed decision making capability is needed where you need reinforcement learning kind of an approaches for swarm. And then we talked about where the world is moving towards. We are not only looking at a visual sensor to do the perception, we are combining vision and language to understand. We are not stopping there, vision and language to understand, we are combining vision and language to get the actions. Trying to build the foundation models, trying to get this foundation model to be having a general intelligence such that it can be applied for different tasks at different domains. In the next class, we will talk more about the module 1, foundations of neural networks. Okay, thank you.